chapter 8, part 5 has three more reactions to cover. But for each of these, we only have one where we need to know the mechanism. So we get a little break on mechanisms here towards the end. Now, the first two are dihydroxylations. We are going to put an OH on either side of the double bond. And the first one we're going to look at is an anti-dihydroxylation. So we will put an alcohol on opposite sides, and then we'll go ahead and look at syn. So the anti-dihydroxylation is done in 2 steps. It's a 1-2. I'll put anti up here. In the first step, we're going to use something called a peroxy acid. And in the second step, we're going to do a little acid workup. Just a little acid and water. So first, let's talk about this. RCO3H is a peroxy acid. This is a new functional group. It is whatever your organic compound is, a carbonyl OOH. So it's like a peroxide and a carboxylic acid had a baby, right? Or smushed together. And you will most frequently see it written like this because it's easier to type. But you should recognize the functional group. And I want you to be familiar with one specific peroxy acid, MCPBA. This is just a specific peroxy acid. It's called metachloroperoxybenzoic acid. You don't need to memorize that. Specific peroxy acid. It's just one of the most common peroxy acids for this method. Now, this is a 2-step process. I'm not going to make you know the mechanism, but I do want you to look at the intermediate. After step 1, with the peroxy acid, and this is why it's an anti-dihydroxylation. When you use your peroxy acid of choice, you get something called an epoxide. This is a cyclic ether. We're going to study them more in chapter 13. And, oh no, it doesn't have a charge. Sorry. It is a 3-membered ring with an oxygen in it. It's not charged, but the carbons attached to the oxygen are electrophilic, right? For this, because they are attached to a more electronegative element. And so when you add the acid, you do get an SN2 ring opening, and then there's some protonation steps. We aren't going to worry about this mechanism until Unit 4, but I do want you to know about this epoxide intermediate. Right, and so we're going to kind of draw this down here because I didn't leave myself room. But the other OH, whichever side it adds to, it's going to be the opposite face of the ring from the OH that was already, from the oxygen that was already there in the epoxide. So you get a diol, right? So an alcohol is an ol, an OL, and you get 2 of them, so it's a diol. It goes through this is why I'm not going to ask you to know the mechanism. It has a unique pattern, right? You are getting an attack, a proton transfer, things are rearranging. It is really interesting, kind of fun to look at. Do not want you to worry about memorizing it. It inserts one of the oxygens from the peroxy acid and makes an epoxide. This right here is a picture of MCPBA, metachlorobenzoic peroxy acid. If you just know that acronym, you should be good. You can look at the mechanism of taking the epoxide to the anti-diol. I will not ask you to provide this mechanism until chapter 13. But if you're interested, it's very similar to what we looked at with the bromonium ion. You just have to have some additional proton transfers. if you notice, we've seen these little 3-membered ring intermediates quite a few times, right? They're really useful. It keeps rearrangements from occurring. It gives you reliable, predictable anti-stereochemistry. They are very reactive, right? The ring strain is pretty high in a 3-membered ring. So they're very reactive intermediates, so it keeps the reaction going. And it's a feature in several reactions we've covered. I have a feeling, yes, if we make an anti-diol, well, what if I want to make a syn-diol? Syn-dihydroxylation. Well, I'm a control freak. I am an organic chemist, so that is kind of goes without saying. If I want to add my alcohols to the same side, I can do it. There are 2 different reagents that are useful. And I want you to know osmium tetroxide. And let's just put like a stand-in squiggly line here. Osmium tetroxide is often followed by some other reagent to finish the reaction. Whatever it is, the OSO4 is what I want you to memorize, right? If you see something else listed, but it's with osmium tetroxide, it is giving you a syn-diol. So one of the things that can be followed with is sodium sulfite, sodium bisulfite. There's also a compound called NMO. You could also follow it up with a peroxide. There's lots of different options, but notice at the end of the day, you're getting a syn-diol in all of them, right? But the thing that is the same in all of them is the OSO4. This is the only reaction you're going to use osmium in for the whole year of organic chemistry. So it stands out. And if you look at the mechanism, I'm not going to require you to know the cyclic osmate ester intermediate. But if you think about how this works, the osmium has 4 oxygens around it, and both of them go on in one step. So similar to that catalytic hydrogenation where both hydrogens go on at the same time on the same face of the double bond, the osmium tetroxide works similarly, right? Both oxygens come to that double bond at the same time. So just based on geometry and space, they have to go on the same side. The other option, and so I guess we should draw this as a ring, right? Osmium tetroxide. It's going to put those OHs, either both wedge or both dash. In this case, it's a meso compound, so it's just one. If it was asymmetric, it would be this plus an enantiomer. Another set of reagents that can do the same thing is potassium permanganate. So you would use KMNO4 followed by sodium hydroxide. So it may be numbered, it may not, but it would be like an NaOH. And it is important that this is all cold. We're going to see in a minute why when you heat it up, you could get different products. But osmium tetroxide and KMNO4 can, in cold conditions, can both give you Syn-dihydroxylation. And if you look at the structure of the permanganate ion, that manganese is between 4 oxygens, it goes through very, very similar steps to the osmium tetroxide. Now, why am I teaching you 2 things that can do the same thing? Well, because as organic chemists, we have to deal with that. There are a lot of different options. In fact, there's probably more than just this. But it allows us to talk about our choices. When you come across reactions like this, where you have multiple choices, there might be the obvious, well, I have permanganate in the lab and osmium tetroxide is expensive, so I may want to just go with permanganate. But then and osmium is toxic. So why would anybody ever want to use this? Well, because one, the permanganate can be difficult to stop at the diol. It could also react with other functional groups that you have. And maybe it doesn't give as good a yields, and osmium gives a great yield. You know, if your starting material is really expensive or it took you months to make, you may want to go the expensive toxic route that gives you a really good yield. Or if it's really easy to make this and you can make lots of it so the yield isn't super important, maybe going the cheaper, less toxic route is the way to go. So these are practical decisions we have to make as organic chemists. And so knowing multiple reactions that do similar things, it's kind of part of the job, right? So I typically will use the osmium tetroxide, but you may come across practice problems where permanganate comes up, and I want you to be prepared for it. Now, we have two ways to add oxygen. These are both called oxidation reactions as well as addition reactions, but we're going to move into our one and only non-addition reaction, but it is also an oxidation. So I do want to talk a minute about oxidation versus reduction. You learned about this in Gen Chem, and nothing I am teaching you is going against what those words mean. Oxidation is loss, reduction is gain, but we deal with such a small portion of the periodic table, we tend to make some generalities. We know that the term oxidation does not just mean increasing bonds to oxygen, because there's lots of oxidation reactions that don't have oxygen in them. But so frequently in organic chemistry, we are dealing with oxygen that when we see those reactions where we increase carbon's bonds to oxygen, know that we are talking about an oxidation. And so while this is an oxidation reaction, we're going from carbon-carbon bonds to carbon-oxygen bonds. We are increasing the amount of oxidation we are going to do when we go into oxidative cleavage. So we're actually going to take a carbon-carbon double bond and we are going to cut it down the middle through an oxidative process that is going to make carbonyls. Now it's going to make aldehydes and or ketones. It depends on what these groups are. And it is another two-step process. This is also referred to as, let me see if I can, there we go. It is referred to as oxidative cleavage because through an oxidation reaction, we are cleaving that bond. But it is also, the specific reaction we're looking at is known as ozonloysis. So we are using ozone to lyse or cut this bond. So ozone is the first step, O3. And in the second step, we just need a reducing agent. For oxidative cleavage of double bonds, we use something called DMS. DMS and O3. So O3 is ozone. DMS is dimethyl sulfide. So you may also just see it written as CH3SCH3. Typically it is abbreviated. It is two steps, so the 1 and the 2 are important. You don't put all of it together in one pot and mix it up. You do the reaction with ozone, and then you use the DMS. There is another interesting mechanism that if you are feeling really excited about mechanistic steps, have at it. It goes through a cool ozonide intermediate that rearranges into a different ozonide intermediate. But the complexity of this mechanism, I think, is a little bit above where I need y'all to be right now. So you are not responsible for this mechanism either. I want you to be able to practice predicting products or looking at the products and going backwards. And so I don't want you to worry too much about the mechanism here. I will provide you guys with a study guide probably after a few days into this unit, where I will list out all of the reactions you need to know, along with which mechanisms I expect you to know. So let's do a little practice here. That is going a little too far right off the bat, so let's do a couple of easy ones here. Let's go ahead and do kind of an asymmetric one. 103 to DMS. And then let's look at an interesting cyclic example. All right, so when we are cleaving this bond, we are cleanly breaking that CC double bond. Everything on the left stays together, so that's 1, 2, 3 carbons. There was a hydrogen on the other side, so we are going to make an aldehyde. And then everything on the right stays together, so that's 1, 2, 3 carbons. That's going to make a ketone. Right? I could, if you don't like how I switched it up, we could keep it in that same orientation. That's fine. But we would make a 3-carbon aldehyde and a 3-carbon ketone. We don't lose any carbon. So if I had 1, 2, 3, 4, 5, 6, I should have 1, 2, 3, 4, 5, 6. I shouldn't lose or gain carbons. Then let's think about what happens when that double bond is in a ring. We do exactly the same thing. We cut that double bond. But are we going to get 2 products? Well, no. It's like in some of your examples in chapter 7. If the leaving group is attached to another part of the molecule, then it's just going to open the ring, right? It's not going to make 2 different products. It doesn't cut all the way through both sides of the ring. It just cuts through the double bond. So what I like to do with these is kind of keep it in the same order. I just make it a little bit bigger or lean one bond out a little bit. So I have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. On the left side of the little line I drew, I have a ketone. And then on the right side, I'm going to make an aldehyde because there is a hydrogen right there. All right, so sometimes with oxidative cleavage, you get multiple products. Sometimes you get one product with multiple carbonyls because it was a ring. Which is a nice segue into this crazy problem over here on the left side of your screen. There are 4 carbonyls, but it is 1 molecule. So it definitely had to be a ring or a multiple ring structure. Something that's really helpful to know is that 5 and 6 membered rings are going to be the most stable. So we're going to try to make rings of a reasonable size. We know that if we're going backwards, the carbons that are in the carbonyls were the carbons that were connected to each other. So we have 4 carbonyl carbons. So we had 2 double bonds. Let's try to connect them in a way that makes stable rings. So 1, 2, 3 is too close. But 1, 2, 3, 4, 5, 6 is a good distance. So these 2 could have been connected. So what I'm going to do is I'm going to number these. You number them, letter them, give them a name. Just keep track of them somehow. 7, 8, 9. So I'm going to say that 1 and 6 had to be connected because I know a 6-membered ring is pretty stable. So I'm going to number, 1, 2, 3, 4, 5, and 6. So that double bond had to be between 1 and 6 because 1 and 6 are now carbonyls. Carbon 3 and carbon 9 would then be the other ring. So it would have been double bonded to each other. So it would be 1, 2, 3, 4, 5, a 5-membered ring. So if 3 and 9 were attached, I'm just going to put this out here. Okay, there was a double bond to carbon 9. Well, 3 is also still attached to 4. 4 is also still attached to 6, 7, and 8. And then 8 and 9 are still attached. All right, so it's going to be a 1, 2, 3, 4, 5. Have I gotten too many? So if this is 4, 6, 7, 8, and 9. I'm miscounting something, aren't I? 3, 4, 6, 7, 8, 9. 3, 4. Is 6. 6 is up here. What am I doing? So sorry. Let me erase this side of the ring. 4 is right here. And then this is 6. God, I'm doing the same thing. I'm so sorry. Let me just erase this. 1, 2, 3, 4, 5, 6. There's 6. 7, 8, 9. 3 and 9 are attached. So if this is 9, I'm also going to attach this ring. 3, 4, 7, 8, 9. 3, 4, 7, 8, 9. There we go. Don't add or subtract carbons here. With an oxidative cleavage, all of the carbons are maintained. This is a challenge problem. For sure. This is going to be a more difficult one. I have put practice problems of differing levels in your homework. There is also a practice set or 2 on eCampus for you. And that is all of the... I'm sorry, that is all of the reactions in Chapter 8. I say that like it's not many. There are a lot of reactions in Chapter 8. There are review pages. We're going to go through this one-step synthesis in the last video. I put a spider diagram up on eCampus for you. Klein has lots of good summary figures. If you go into your Wiley Plus and go into the chapter, go towards the end, there's a lot of great summary slides. You need to start working immediately on memorizing reagents. Unlike Chapter 7, the reagents all look very different, which is helpful. 7 can be confusing because all of the reagents can look so similar. But there are more, right? So you need to work on committing those to memory. So if you're a note card person, that is something I would recommend doing right away. Chapter 9 is going to have more reactions. So we want to stay on top of that. When you are writing those reactions out, keep in mind your regiochemistry, right? Mark and anti-mark. And then stereochemistry with syn or anti is important for a lot of your reactions. The last section will cover 1 and 2 step synthesis problems, and I'll be back with that.